We had a good conference so far? Love it. All right. XML. So don't fall asleep just yet. Yeah. So the impetus for this talk was I was working in a company that used to do a lot of integrations with airlines. And so there was a lot of XML back and forth being passed around. And some of the documents were like very, very big. And at the time when I joined, there was definitely a sense that that XML parsing wasn't very quick, and it wasn't being very efficient with memory either. So I was part of a team to try and help improve that situation. The parsing that was happening was, we had a SAX parser, okay? That stands for Simple API for XML. It's not a great name because it doesn't tell you anything about what the parser actually does, right? But SAX parsing is this idea of we had something that would churn through the XML binary, and when it encountered elements, it would call the callback module that you provided and give you the opportunity to do different things based on what it had just seen, right? So, for example, you would see the node name and maybe a list of attributes for that node in the XML. You'd get called with that information, like, hey, here's the node name, here's the attributes that you have. Do what you want with it. And so normally what you would do is build up what is kind of like a DOM, okay? And I say DOM, like I'm using the term loosely there because obviously we don't have objects in Elixir, but you get the idea, right? We're going from an unstructured sort of binary string, essentially, to a structured thing, right, that we can then query to get values out of. So the architecture we kind of had was something like this. We had Saxy, which is the thing that's not emitting the event, calling the callback. It's almost like lexing, right? It goes through and says, hey, I found a node, here's its attributes, calls you callback, right? Then we had something that, a callback module that implemented building up a DOM based on the information that was in the XML, right? The structure we use for that DOM is XML. This is built into Erlang, actually, interestingly. So Erlang ships with functions to create and sort of like query, manipulate that XML, which is basically a tuple-based structured representation of XML, right? So Saxy would happen, we'd build up this like DOM, then we would apply XPath queries to that DOM to extract the data that we wanted from it, right? Yeah, so when I joined, the sense in the team was that XPath was the slow bit, and that like the Saxy to the XML thing, that was like pretty quick, so it kind of wasn't a problem. And I think if we had been thinking about like hotspot programming, you know, trying to tune performance by looking at the slowest bits, we might have been tempted just to look straight at this and be like, hey, let's improve this, XPath's slow, can we make a faster XPath querier? I think that would have been a mistake. So luckily, we had the sort of foresight, I guess, to look at it more holistically and see what do we actually need from this data that we're getting and what are the implications of that, right? So the approach what we ended up realizing is that we just don't need XPath, okay? XPath is like quite a sophisticated query language. It allows you to do things like find all of the children of this particular node and like group them together. Lots of quite sophisticated queries. I guess if you've ever done CSS like selectors, that's kind of a version of XPath in a weird way. But yeah, anyway, it's way more sort of powerful than what we actually needed because most of what it boiled down to was you either wanted an attribute value or the text inside of a node, right? Like the children of a node. And that was basically it. So, and there are other actual problems with XPath too. For example, if you have a node in an XPath that doesn't exist, you're just going to be returned nil. And you're not given much information about where in that path something went wrong, you know, where your expectations deviated from what you were expecting. You just don't get much information, which makes it hard to debug and all sorts of problems like that. So we decided to cut out. And the other thing was actually the XML, as far as I can tell, its structure is made so that XPath queries are possible on it. But in doing that, at least the way it's currently implemented, it seems to be very like bloated. It used a lot of memory, right? For the size of the document that you had, the XML would be many times that. And that was kind of problematic. So we cut both of those out and instead went for something a little bit simpler. We had Saxy. We still had that, calling our callback module that we implemented, but the DOM we built up this time was something just called simple form. And simple form is a very simple tuple-based representation that just has the node name, list of attributes, and then a list of children. Children can be either text, right, like a string, or more of these tuples itself. So it's kind of recursive, right? That's the minimal amount that you can store without losing information, right? Whereas, as far as I understand, XML has a lot more in it to, again, support these XPath queries, which we kind of just didn't need. So that's a simple form. And then what we ended up doing was like implementing our own querying on top of that simple form structure. And to aid that process, I wrote this data schema library. You can think of, there's a few libraries kind of like this, I guess, floating around in the ecosystem. But the idea here was it's similar to ecto-embedded schemas, right, but applicable to any sort of input source. So in our case, that simple form DOM that we had, we could use that and query it by writing schemas that know how to take that DOM and transform it into structs. So if we have a look at a simple example here, this is how you would define a schema. It's a macro. And I'm going to just like comment out loads of stuff so we can focus on the things that are important here. This is the name of the key in a struct, right, that we're eventually going to create. This here is a path to some input in the data that we're transforming into a struct, right? And then this here is like a casting function. So the idea here is something's going to go to the end of the path, right, in the simple form DOM that we have. It's going to get a value that's there. It's going to pass it into the string cast function. That can be anything we want to do. And then it's going to take that result, the result of casting, and if everything went well and it wasn't an error, we put it as the value under this key kind of thing. So it's just like a generalized version of, applying ecto-embedded schemas, for example, to like JSON. It's that, but generalized to anything. So how does the library understand how to apply the path? Well, it doesn't, right? You do. So you implement this accessor here. And again, this is a callback module that when we're creating these structs, we'll be given the path for the specific field. So here, airline customer name, that's a path. It'll be given that, and it will be given the input data, which in our case is a DOM, and then you implement applying one to the other to extract a value, right? So in that way, it's got the most flexibility, right? Any developer can make any schema for anything, as long as you teach the library how to apply the path to the schema. So your path can be anything, your input data can be anything, and you can make structs out of it, which is kind of cool. So the real win in terms of the XML parsing was just having that smaller DOM enabled faster querying, and it turned out to be a lot simpler than XPath was, right? And in the benchmarks and everything we had, like it really was 10 times faster and 10 times less memory, which is a noticeable difference in infrastructure costs. Such was the amount of like XML that was being parsed, right? So cool. So that was a really nice win to kind of have. But when we were doing the project, I just kept thinking there was like more that we could do. But startups being startups and all the rest of it, we kind of ran out of time, and it was no longer the big problem. So we took the win that we got and just moved on. But when I left the company, I was like, I'd like to go look back at this because I think there's more there. So yeah, that was the question I had. But I was no longer working in XML, and XML is XML. I mean, whatever. So I thought, let's see if I can take some of the ideas that I had and this extra question that I wanted to explore, and let's apply it to JSON instead. So let's design a JSON parser together, because we'll need that first before we can go extra with it, right? So the first constraint is that we know nothing, which is a rule for life, I think. And then the next thing that we should think about is like whatever we do know we should share, so we shouldn't be like hiding information. So the way I think about this is that callback approach that we saw in the SACS parser, I think that's really powerful because it gives us the most flexibility to the caller of the library, right? You, the developer, know best what you want to happen with floats in JSON, for example. Like maybe you want it to be a string, maybe you want it to be casted decimal, maybe you want it as a float, maybe you want to round it and have it be an integer, right? Without having a really hairy like API or having to thread options all the way down in some weird way, callbacks are probably the best way you're going to get that. So our JSON parser is going to be callback based. You're going to provide ways to deal with when you see different values in the JSON, right? And the way it's going to work is we're going to call your function with the original JSON and then the start and end index of the things that we care about, right? Of the values that we see. And the reason we do that is then it's completely up to you whether you want to copy the section of the JSON that you care about. Like if you have a string, you could copy it or you could refer to it. It's like completely up to the caller what exactly happens. And then the second part, like, we just want good errors, right? If we're capable of giving them, we should definitely be as clear as possible. So these are the kind of like guiding ideas I had going into writing this JSON parser. Let's see what we can do. So this is the API for the parse function that we might imagine. So obviously we've got the JSON that we would like to parse. We have the handler. This is the callback module that you're going to provide yourselves to build up the DOM or whatever you want your JSON to become, right? Then we have the start index. So this is the index of the head, like the first byte of that JSON that we're parsing. I think it'll make a bit more sense why we have that in a minute when we look at a bit more of the other stuff. But it allows, we're basically maintaining a pointer to the thing that we're looking at in that JSON as we parse it, right? And then we have an accumulator, which is the result of the handler function. So it's kind of like the DOM we're building. Normally in JSON, you just take it and turn it into like an Elixir map because there's a pretty direct translation, right, from a JSON object to an Elixir map. But again, like that is an assumption that's built into most of the JSON parsers that we use, which is that you want your objects to be maps in Elixir. And that might not be the case. Maybe you want it to be a keyword list or anything else, right? So the handler itself, the whole like SACS parsers and this kind of like idea, there's a lot of flexibility in different implementations have different opinions about what should go in it, right? So here, the API is basically, I see a true value or a false or a null or a string, integer float, the start of an object, the end of an object, etc. All of the things that can be in JSON has a corresponding callback function. Like I said, we get the JSON, the start index, and the end index, and then the accumulator, and it's on you to return a new accumulator based on whatever you want to do with the stuff that was in there, right? Cool, so we've got like the rough high-level overview of what we were trying to build here. Let's look at how we might do that. So if you've ever done data, has anyone done data parsing in Elixir? Any hands? Yeah, a couple of hands, cool. So we know about binary pattern matching, right? It's awesome, it's great. It's one of the best things in Erlang, I think. So you maybe like read about parsing combinators and you're like, I know what I'll do. I'll do this. So here what we're doing is saying, if it's like a case that we have. If the first character in the JSON that we're parsing is a quotation mark, we're going to assume that what we're trying to parse here is a string, right? So this current index is like the count. It's the index of the head of the JSON that we're passing, in this case, the quotation mark, right? And essentially, if we see the quotation mark, we start treating it as if we're passing a string. So we call another function that maybe does like string escaping or just checks that it's valid generally, that kind of thing, has like a closing quotation mark the way you would expect. We increment the index like you would expect to, and we pass in the handler so that if we get a valid string at the end of it, we can call that and say, hey, we found a string, here it is, kind of thing. Here's the start and end index for it, right? Then the accumulator so that the handler can get that, right? And then we just like continue passing the rest of the thing. So don't do this. And there's a really big reason why this is not a good idea. And it's the fact that we returned a string from that nested function there. It's a bit of a gotcha, if you ask me, because I had always heard that pattern matching, binary pattern matching was kind of quick. But there's problems with it. And the big issue is the match context. So there is an optimization in Erlang that allows you to avoid allocating new strings when you're doing binary pattern matching. But it only applies in some situations. It only applies when it knows that you're not kind of using the thing that you've pattern matched out. So in this example, we've taken rest out of it. We've passed it into another function. That's done something with it and probably moved further along the JSON string and returned you another thing. And because it's returning you that string, it gets allocated, right? And so you miss out on the opportunity to reuse the match context, okay? How do you know if you've done that? Well, there is a compiler option that you can use, bin opt info, and it will give you really helpful warnings like this. This is a good warning. This is what you want to see. Optimize, match context, reuse. That means quick, right? This is like less good. This means there's something to look at if you can. Like binary created is used, or binary is passed as multiple. There are a couple other warnings in that ilk that kind of just give you an indication there might be something to improve if you can. But I remember seeing this and reading about it and be like, yeah, I kind of get it, but like what? Like, how can you write a parser? I need the string, parser combinators, like what's going on? It really melted my brain for a minute. But the big change is our parse string function, instead of returning the rest of the JSON that we need to parse, all we're returning now is the end index. So it's going to go through, and if it is successful, it finds the closing quotation mark. It kind of like returns the number, the index of that. Then we can do this. So binary size allows you to say, you can provide a number to it, okay, like 10. And what it will do is allocate, in this example, we have skip as the variable. It will get the first 10 bytes, right, of the binary, and save that into the variable, like skip. So what this effectively does here is skips over the string that we just passed, because we're kind of done with it. Now we have the end index. We can call our handler, right, passing in the current index and the end index, and the accumulator as we expect, and pattern match. If there's an error, then we error. Otherwise, we continue with the rest of the parsing. And so this match context reuse is actually quite clever because it works on recursive functions. It knows that if parse never actually just returns something that's pattern matched out of the binary, it can keep reusing the match context all the way to the end. Because we never do, because what we return is the accumulator, the match context gets reused and we get this like fast parser because of it, right? And this is just, I found this out. We had a 4 megabyte file. I did a version of it with and version it without. Without match context reuse is about 3.5 times slower, but crucially the memory was 10 times. So it can really make a big difference. So the rules, reuse the match context, and C1. Cool. Yeah, the other thing, callbacks, really good. Just to reiterate these, while I was writing this JSON parser, JCS came across my, psyche. That stands for JSON Canonicalization Schema, which I can just about say. But that is a sort of convention to try and parse JSON in a specific way to help with like security. And currently the JSON parsing that we all use, probably the JSON library, JASON, can't enable this because it doesn't have this callback callers and control like approach to it all. And similarly, the callbacks allow like per field data casting, and the caller decides, do they copy the binary or do they refer to it? All this kind of stuff just comes for free. And also, when you have this callback approach, you can even have like a pause, resume parser. And the way we can do that is, if you remember when we call this handler, we already pat match on an error, so we can stop straight away if the callback module says, hey, this is something wrong. We could add another case that just says, hey, if you return halt and an accumulator, we save the rest of the work to be done into a continuation. We return you that with the accumulator, and then later on at any point in time, you can just recall to resume it with the accumulator again and like carry on with the rest of it. So that's kind of like neat too. So constraints, we know nothing. We're not assuming anything. If we use callbacks, nice. So what the second part of it, which was what we do know we share, we want good errors. So here's an example of one of the errors that we provide. Invalid decimal number, nice and clear. That too is a zero-based index of the character that went wrong. So in this example, you know, the plus is invalid. So we have 0, 1, 2. The 2 points to that plus character. Here we have the trailing comma, and we have unclosed array, for example. This one's kind of interesting too, because normally when you are parsing like these nested structures, right, the way you do that is you use a stack. And what you do is when you open something like an object, you put something on the top of the stack. Then you open an array, you'd put that on top of it. And then when you close it, you pop it off the top, right? And if you are like closing an array and the top of your stack is an array, everything's good. If you close an array, but the top of your stack is an object, then you've seen something in the wrong order and it doesn't kind of work out, right? But in the library that I wrote, I actually use a slightly like different way of doing that, which is just that if you have two things consecutively, rather than stacking two things on top of the stack or more, you can just keep a count of them. And then instead of you decrement that count, and when it's less than 0, pop the whole thing off. So I could imagine some cases where that maybe saves you a bit of memory. I don't know if it actually does though, but it's kind of cool. Anyway, so I wrote this. We have a JSON callback-based parser thing that emits start and end indexes for values that you might care about, right? And yeah, we have like nice errors in that, which have some interesting implications. But all of that just brings us back to the original question I had when we finished the XML project, which was, can we extend the idea of having the smaller DOM even further? So the thing that struck me was like, look, we've done this work of defining these schemas that have exactly what we want from the XML. So why are we adding like all of these other values in that we know we don't want, we don't care about them? So these here, whether we're talking about JSON or XML, they're defining the values that we care about seeing in the response that we have. So if you think back to the XML, we would create, if there were other things in the XML, we would create a DOM with all of it, and then we would query it using these paths. But it's like, if we can find a way to feed this into the parser itself, we could theoretically not even build the DOM for the elements we don't care about, right? So that's the approach that I was trying to look at. So let's imagine we have this JSON as an example. We don't care about this field, right? And we also don't care about any of its children, therefore. So what we want to be able to do is when the callback gets called and we see the key is ignored, we want to check like a schema, right? And say, are you something that we care about, yes or no? If it's not, we want to like start skipping and basically ignore everything, all of these children, right until we get to the closing thing here. At that point, we can stop skipping and say, right, now we can check our schema again, because it might be something that we care about. So we get airline, that is something that's in our schema, then we want to like start building the DOM for that element, right? So there's kind of, yeah, it's kind of trickier than it maybe seems. What you need is like an interesting data structure design problem, honestly, to think about what is an efficient way to have a schema that we can query into when we're getting lists of events like this. There's two broad ideas that I've had around this. I'm sure there's more. It's something that I don't feel like I've really bottomed out, but it's definitely interesting to think about. So one option is to have your schema be something like this, right? It maps roughly to what we expect the JSON to look like, right? So here what I'm saying is, if we get that this ignore key first, ignored, we would do like a map.get on this schema here. It would return nil because it's not in the schema. So then we'd know, okay, cool, we can skip this and skip it until we don't, skip all its children kind of thing. But if you saw airline, you would map.get, right? And then you'd get like a nested schema. So then you'd know, okay, cool. We care about something with, a child of it somewhere. We eventually care about the value down there somewhere. So make sure you keep this in, right? And then, that continues until you get to like a leaf value where you can say, cool, chuck that in the schema, away we go, right? But the tricky thing with this is, like we can have siblings, right, in maps, so customer and ticket there. So we get all the way down here with the map.get, but it's like we need to be able to move back up, right? The schema has to move in lockstep with the events that we're emitting. So as we travel through the JSON and see different elements, the schema sort of has to move along with it, right? So we have to be able to go back up. We have to be able to go back to get ticket, right? And so to do this, there are like two broad approaches that I can think of. The first one is the as you get events, right? I've seen this element, I've seen this key, I've seen this key. You just maintain a path of where you're pointed to currently. And then you apply that to the schema each time fresh and say, is this in there, is this in there, is this in there, right? Or the other approach is to use a zipper data structure, which I'll get into now. So the absolute path thing is just like we see airline, we remember that. And then we see customer, we prepend it onto there. And we say, now we're an airline customer, right? And then it's like airline customer name, so on, so on, so on. And then you can just keep, each time you extend the path, check your schema, using like access even or something. And if you're returned a value, then you know that it's something you care about. But the issue there is that it gets a little bit more complicated than you might think because lists require special syntax, because your schema is never going to be enumerating all of the indexes in the list because it will be unknown, right? So if you have a list of things in your JSON, you don't know how many elements are in that list. So your path isn't able to be like 0, 1 to 10 or whatever. You want something like, all. So there's this tricky kind of little problem in there that you have to like iron out in a nice way if you're going to take that approach, right? The zipper approach, let's first explain what a zipper is with the list. So if you imagine this list, if we're iterating from like 1 to 2, normally you see 1 and we see 2. Instead of like having a list, what you do is turn it into a tuple of 2 lists, right? And when you traverse through it from 1 to 2, what you do is take 2 and prepend it into that second list over there. So that goes into here like this. And then the focus, like the element that you're on currently, is always the head of that left list. Or is it? Yeah, left list as you're looking at it, yeah. It's always this. And what that does is you haven't lost information when you traverse, which means that you can now move back by moving the 2 back that way, right? So it gives you this like focus that you can move back and forward on easily, which is kind of what we needed. Remember how we were saying that we needed to like go back up kind of thing. But so these zipper structures, because we're in functional languages, they give us a way to step back up or undo almost. But the thing is, we're talking about nested trees, like maps within maps with arrays in them. So you kind of have to take this and make it 3D, which is just so. Yeah, and there are some good existing zipper implementations in Elixir already. I just don't know what their performance characteristics are yet. So I don't know if this approach is better or worse. And I know that the zipper would have to also support like writing data and stuff. So some extra things there. Okay, so how does skipping work? Let's assume that we have that schema thing working in some way, right? The way it would work is, and we're going to skip over a lot of this code, our callback function is getting called now, right? We've been given an object key. We extract the key from the original binary, and we have some way, right, of asking the schema, hey, do you have this key inside you? Is this something that you care about? If it is, cool, save it to the DOM. If it's not, what do? Well, we just prepend onto the accumulator this skip element, right? So what are the numbers? Well, if you're skipping something that has an object under it, you're going to want to keep account of how many nested objects there are under it so that you know at what point you can stop skipping again. So this is an array count and this is an object count. Because our top-level parser bit, the Elixir thing, right, the thing that calls our callback, that is checking already that the JSON document is valid. We don't have to do anything more sophisticated than have two numbers here that just increment and decrement as we open and close objects. So we can just have them be like object counts. And then a callback, so say we get a callback that says, hey, we found false in this JSON document. Here are the start and end indexes for it. We can just have a case at the top that says, hey, if we're skipping right now, then don't do anything. Just continue, right? And in that way, you kind of like save some work. And that's true for every possibility, like starting an array, starting an object, so on, so on, so on. If you start an object when you're already skipping, you want to increment the object depth. So this bit here says like add 1 to the object depth because we've opened an array when we're already skipping. So just make sure that we're counting how many we've opened. And then when you close it, what you're doing is you subtract 1 from the object depth. If both array and object are 0 or less, like it means that you've closed everything that was opened. And so pop off that stop skipping completely, pop that skip tag off. Otherwise, just continue with that new object depth of like it decremented by 1. Cool. Probably quite tricky to get used to, but maybe if you're watching on YouTube, you can pause it and think about it a bit. But does this work? Well, yes, luckily. This is an example of a benchmark where what I've done is parsed like quite a large document and then extracted just a small part of that document from it. And like, it doesn't take a genius to figure out that it would be quicker, right? As long as the parser itself isn't slower, you're doing less work because you're not casting all these values that you ultimately throw away. So we can construct examples that beat JSON and Poison because of this like time saving. Cool. And the memory usage there seems a little bit high to me. I think there is ways to bring that down. But that's a trade-off you could think of too. Maybe you're fine spending some memory to make it go faster. Who knows? But the thought occurred to me when I was doing this was like, wait, is this just not pattern matching? I don't know. So if I was to continue with this, that would be the thought that was in my head and probably the area that I'd look into more. It feels like what we're doing is pattern matching on what we expect the JSON to be, but like with events in there somehow. It's like a bit crazy. But there is some good news. As I was doing this talk, I tweeted out some benchmarks and things. Yeah, and some people were excited. But Michael Muscala, who is the author of the JSON library that you all use, I guarantee you it, he's already implementing some of these ideas in OTP core. So this is really, really good for everyone. It means it's available to all of the Bean languages. He's using some really cool, sophisticated, fast UTF-8 checking and things like that, that just makes the parser overall quicker. But it's also implemented in this callback approach where you have hooks to be able to implement your own ways of taking values and casting them to whatever you want, kind of thing. So what I would love to do is when this comes out, and probably in OTP's 27, is try and take that later idea that we had. Is there a way to have schemas be fed into this parser so that we can eliminate things that we don't even care about seeing? Yeah, so I don't know. Future should be exciting. We'll see. But that's all I have right now. So thanks for listening.
Thank you, Adam. That's going to take me some time to digest and look through a few times, but I'm really excited about it. Any questions from the audience online or here?
Awesome talk, Adam. I don't know if you know, but the callbacks way of doing things is super compatible with. So if you really need performance, maybe like JSON is doing non-native. So if you're doing like the VM versions of JSON parsing is like adding latency, which for some applications is real. And you have to fall back to like a NIF.
Right.
Dan Lemire has recently come out with a bunch of SIMD-based like JSON parsers, and they fit really well into that sort of API. And also, there's now like a lazy JSON where you can just say, ignore everything until you get to this JSON path, which I think you covered as well. And so it will do exactly what you did, which is like here's the index in the string where you should start looking at things.
Yes.
So, yeah, really loved it.
Yeah, awesome. I mean, that's what's kind of fascinating about it. Yeah. The other thing too that I was hoping is that I imagined this kind of like self-healing parser as well, where like, because we tell you the exact byte that's broken, it's like, is there a world where you could just delete the byte and continue with the rest of the JSON and see if it worked? Like, that was kind of fascinating too. But yeah, the SIMD stuff looks really incredible, especially with the callback stuff, like I was saying about it being pause resume. That made me think of NIFs immediately, right? Like if you're being a good citizen of the beam, you want to yield control back to the beam. Being able to do that in a way that seemed like maybe that's a cool little use case in there. So yeah, who knows? But.
Anybody else? Any other questions?
This is cool talk. Did you explore using code generation to like generate a parser with macros that would parse a particular schema?
Yeah, so remember that data schema stuff? Well, okay, there's two answers here. So, no, is the short answer. Certainly not for, like, you're thinking of like Nimble CSV, that kind of ilk, maybe, or? Yeah, I haven't really explored it. It's definitely something to be there. One thing I did look at in the old company that I worked at was these schemas that we've had. There was some interesting data generation you could do around that. For example, you could take an example XML or JSON document, iterate over it, figure out all of the fields are in there, and then generate the schema definition for everything that was in that. And then you could, as a developer, go through and delete things that you didn't want or whatever, or change the casting functions, do whatever you want. But it would give you like some kind of the way there. Also, there are some interesting things you can do here with the path itself. For example, you can't see it here, but the schemas, you can have like has many fields or lists of things. And if your path doesn't, says it should be a list when it isn't or whatever, you can get compile time checks essentially that help guide the developer and make the developer experience a bit better. But yeah, I don't know if that answers your question, probably not, but yeah, nice.
We have time for one more question. We got a hand up.
So for something like this, one of the things I found has always been fun is trying to get quality data to do benchmarking on. And I was wondering if you had any adventures in like generating massive like gobs of like JSON to throw at this, and make sure that you've got a document structure that's interesting enough to really exercise different parts of your approach.
Yeah, it's a cool problem. I originally experimented with this stuff with a Lisp parser that was trying to do the same thing, where it had like events and you would implement callback. And that was fun because I wrote a thing that generated valid AST Lisp stuff. This time I just went to the JSON library and borrowed the benchmarks they did. So recommend that, yeah.
Awesome. Thank you, Adam. Appreciate it.